Okay, so I'd like to look at a ladder circuit, an infinite ladder circuit. Now this is a problem I really, really like. I think just about everybody really, really likes it. In part because there's a really easy way to do this. And I think I may have shown you this in class, or will show you this in class, since this is technically before my lecture to you. I've already written it, but that doesn't mean that it's not. Actually, it's already online. So if you want to get a head start, you should realize that I'm usually putting these lectures up online about a week before I actually talk about them. And so I think that I have in there the quick and dirty way of doing this. So you can look at that, but that's not really a part of this course. That's something that's in a circuit course, a circuit analysis course possibly, in one of the early introductory chapters or in our Physics 3 class. And that's a really simple way of doing it. But I'd like to do it with Kirchoff's laws. They are a part of this course. And I think that this helps understand will help you both understand how to use those Kirchoff's laws, and it will help you understand the sort of trick, right? So this will show you why the trick isn't just a trick. It's a real important way of arguing. Whereas just invoking that trick, like we did in class, that does not seem to me to be a really good way to get you to learn about either the circuits or about the nature of this infinite ladder, right? The nature of this translational symmetry that we can use to help solve the problem. By looking at this with Kirchoff's laws, in fact, I think we can look at both in such a way that it will help you with your homework and help you not just with your homework for this section, but also for the previous section where we looked at Kirchoff's loop rule originally. So I think it's going to be pretty fun, but we have to do the same old things that we always do, right? And define exactly what it is we have. And we have this ladder consisting of these two types of resistors. Along here, there's a resistor R prime along this top line, and it just keeps on going down. So we go R to R prime, we lose a little bit of voltage. R, or 0 to 1, 1 to 2, we lose a proportionate amount of voltage, so forth and so on. So we just keep on going on this way forever. All right, and then down here we lose the we drop the entire voltage down. So from here to here, we drop the entire voltage, come on back. Here to here, drop the entire voltage of here and come on back. And we have these R's going on as well. So we'll have R prime, down R, across R prime, down R, across R prime, down R, so forth and so on for eternity. And so we want to define the resistance of both of these kinds of resistors and the voltage supplied, the power or the potential supplied by the battery. And I think that's all we really have here, right? All we have to do is find the effective resistance of this circuit. Okay, and like I said, I want to solve this with Kirchoff's laws. We'll also use Ohm's law, and we'll only use the node law for Kirchoff's law, but we'll also use Ohm's law over and over because Ohm's law is very, very useful, especially for this kind of problem. We'll use the boring circuits, Ohm's law, not the interesting, cool physicists' version of Ohm's law, right? Just because the boring version will get us there, and so we'll just use the thing that gets us where we need to go. So the first thing we'll probably do is we'll find the voltage drop over the R prime resistors, or find the voltage at each of the top nodes. Okay, so what we've got here is we have our battery coming in, right, something like that, and then here at node 0, it's gone through zero of these resistors, so it's node 0. We have some voltage V0. Then it goes through some of the voltage goes this way, or some of the current goes this way, some more of it goes that way, and then we have a V1 here, and some current goes this way, some current goes that way. We have a V2 here, so it's gone through 2 of these resistors, and la di da di da, and we've gone through n-1 of these resistors here, and then we go through this nth resistor, and then some of the current goes here, some of the current goes out, but this is the Vn, and then this keeps on going forever. All right, and whatever happens from here to here has to proportionately happen from here to here. So basically what I'm going to say is that if V1 is equal to A V0, then Vn minus 1 is equal, or Vn is equal to A Vn minus 1, right? So whatever happens from here to here has to proportionately happen from here to here because the physical situation is the same, right? I think that makes sense. So if that's what's going on, right, that means that I can take this Vn minus 1 and I say, well, Vn is equal to A squared Vn minus 2, right? Because I can have Vn minus 1 is equal to A Vn minus 2, and put that in here, have A times A Vn minus 2, and I have this. And in fact, you end up going all the way down to Vn is equal to A n over V0. Very, very simple. And V0, of course, is just V, so I can even erase that and just say Vn is equal to AN V, right? So V0 is equal to A to the 0, which is 1 times V, which is exactly what it is, right? This comes up here, comes down here, and comes here. Perfectly sensible. I'm sorry, I'm working this like a board problem instead of the problems up here. But it's so cool. I can't help myself. I want to start, I really want to start. I know you want to do this too. I mean, I'll talk a little bit more and you can do the second part, which is to find the current in each resistor. So I want to find the current in that resistor and in that resistor and in that resistor and in that resistor. So I've got 2 types of resistors, which means I'm going to have to know not only the current from here, the voltage from here to here, which is this voltage, right? This voltage from here to here, the potential difference that's going to go through this resistor is between V0 and 0. And we can look at this as if it's grounded. So we're perfectly fine. So we've got the difference coming up here of V, down here of V, and we're happy and stuck that way. That makes perfect sense. That's Kirchoff's loop rule, right? So in this case, right, what we're going to have to do is we're going to have to say, okay, well, I've got a current coming into this node, so I've got this I to the n minus 1 coming into this node, right? And then coming out of it, I've got my IN, right? And my I bar n. So the IN is the current that goes from a node to ground. I bar n is all the stuff that's left. So this is all the stuff that's going back to the battery. This is the stuff that's left over and is going on to the rest of the circuit. All right. So we have to use this, which tells us that I bar n minus 1 is equal to IN plus I bar n. To find actually part 3, but we want to know what these 2 things are. All right, and to find these 2 things, we use the resistance. Okay, so our resistance tells us the easy part, right, is IN coming down here is equal to Vn, because that's the voltage from here to here, here to here, here to here, over R. That's just Ohm's law, and that tells us that IN is equal to ANV over R. Excuse me. Okay. And from here to here, we have a delta V. So we have the difference between the voltage from here and the voltage here. So that delta V at N, right, from there to there, so this would be delta V1, right, is Vn minus 1, which is equal to AN minus 1 times V, which is equal to AN to the minus 1 times 1 minus A times V. Okay, so this is between here and here. Okay, so actually we should call this V to N minus 1, I'm sorry. So that's going from the N minus 1 to N, so this would be I to the N minus 1. Okay, so that's fine because we can modify that in our heads. So we're going to call I bar N the stuff that doesn't go through, doesn't come down here. Everything that comes in here but doesn't go down here is the I bar N, the leftovers that we keep getting to work with. That's equal to delta Vn over R prime. And that means if this is N minus 1, then this just is N, right? So we have A to the N, 1 minus A V over R prime. Okay, so those are the currents in each resistor. Now we have to come back to this, right? And we want to use these and this, especially this here, to find a relationship between for this drop constant A. So this is just some proportion that I pulled out, right? The voltage after this is proportionately smaller from this number from 0 to 1A. However, how much is that? Yeah, I don't really know, but it doesn't really matter. We're going to solve for that. So we're going to find this relationship for A using Kirchoff's law here, and that's going to use our I bar N. And so first of all, we have I bar N minus 1, which is A to the N minus 1, 1 minus A V over R prime. That's going to be equal to this IN here, which is just this guy here, A to the N V over R, plus A to the N 1 minus A V over R prime, because we have I bar N and I bar N. So we're pretty good with that. I think we're all happy with that, right? So having that, we can put everything together and end up with an equation. So these V's, for example, we can get rid of the V's; those cancel. Get all but one of those A to the N's, right? A to the N minus 1 here, and so we end up with an A here and an A there. And then we're going to have to cross multiply these R's, right? So that we have, let's start with this one. We have 1 minus A times R is equal to A times R prime. And this is going to be plus A times 1 minus A times R. And this can come over here, so we subtract this from both sides. So we have 1 minus A times 1 minus A, so that's going to be equal to So that implies that we have 1 minus a squared r, right, minus a r prime. And that is equal to 0. And using this, we're going to be able to find the constant a. All right, and that's a matter of doing a little bit of work with your quadratic equation. I'm on the fence about doing all that work. It takes about half a page, so I think maybe the best thing to do here is to just sort of set this thing up and say we've solved it. So what we have to do, of course, is to, FOIL all this sort of stuff out. So what I'm going to do is I'm going to divide through by r, and then I'm going to say, okay, I have a squared minus 2. I've got a minus 2a here. I've also got another a here and a minus sign, and that's going to be that's going to be plus r prime over r times a, right? And then we're going to add 1 to it, and that's going to equal 0. And as you can see, that's just a very simple quadratic equation in A. And you can use the quadratic formula if you really, really so desire, and I'd suggest you do this to find that this is equal to a is equal to 1 plus r prime over 2r, excuse me, minus the square root of r prime over 2r squared plus r prime over r. Okay, so that doesn't look really, really great, but if you look at the solutions online, where you have something like if you look at the solutions online, you'll see that if r prime is equal to r, you end up with this 3/2 minus something like the square root of 5 over 2. That's exactly what you get here. All right. So this, like I said, I was thinking about going through that for you and showing you how to use that quadratic formula, but then I remembered that you do it all the time, so you don't really need to be shown. If you have any doubts about this, I encourage you to go ahead and do it. But this is the but using this constant, we're going to be able to get a solution for this. We're not there yet, but we have used our symmetry once. I think we only used the symmetry once. Next, we're going to go ahead and do an infinite sum, right? And after we do that infinite sum, we're going to find R effective. And I think I can do that just on the bottom of this page. So I won't switch pages. I'll just take a little break, maybe get something to soothe my throat, and finish that up for you in just a second, all right? All right, let's see if this actually works, if I can get all of this on this piece of paper here. I think I probably can. There isn't really that much left. So, our last thing here is to sum the currents, okay, and find what the total current is. And then we're going to, after we've summed those currents, we're going to go ahead and we're going to put all of that in with Ohm's law, all right, to find the effective resistance. So what I'm saying here is that the total current that has to come in here, right, all of the current that's coming in here is the current that goes through here, or it goes through here, plus the current that goes through here, the current that goes through here, and so forth and so on, all the way out to infinity. Okay. So coming through here is, you know, some proportion of this, but this stuff here never goes through another resistor. So this just goes back to the battery, and therefore there's no way to double count by adding up these INs, which is another reason why I use the IN here, right? One, it goes with this VN that goes with our proportional drop. The second is that, you know, this guy doesn't double count. These IN bars would double count. If I added them all up, I'd double count on current. So what I'm going to do is I'm just going to add up all of the current that goes through each one of these resistors R, all right, which is sum from n equals 0 to infinity, IN, all right, and then we go ahead and substitute for that IN. Where do we hide it? Up here, right? And so we have AN times V over R. Luckily for us, the V over R is a constant. So n equals 0 to infinity, and we have just this AN. And we love this particular sum. We know what that sum is. That's 1 over 1 minus A, right? So we have V over R times 1 over 1 minus A. Fairly simple result. It's something that we can use readily. So I think we're pretty happy with that. So if we want, then we can find our effective resistance, right? Which is our resistance from here down to here. If I had left this up here, I could show you the resistor, but it's just the resistance of this total voltage drop, right? So that's V over R, the total V over I, the total voltage from the battery over the total current going in. Effective resistance, exactly what we need, right? Let's see, what do we get? Well, we get a V over R over 1 minus A, which is equal to 1 minus A times R, right? And we know what that A is. It's right there. And that's an incredibly dull number, I think. But we've got a 1 out in front and a 1 here, so those cancel. We've got a minus here, that becomes a positive. We've got a plus here, that becomes a minus. So we can call this the square root of R prime over 2R squared plus R prime over R minus R prime over 2R. Okay. Like I said, we can check this against the online solutions that you'll find for R prime equals R rather readily. So this is our answer. It's perfectly natural. It's beautiful. It's a lovely answer. I like that answer. I probably should have been prepared to actually draw it out, but I'm not, because I mean this is a perfect thing with an R prime over R. That's a perfect thing to plot against. But I'll check it against the online answers, which I did already, but using R prime minus R prime over R. So in that case, we have the square root of 1/4, R prime equals R, plus 1, right? Minus 1 all times, R. Forgot to multiply by R. Excuse me, I'm sorry. We've got all that multiplied by R, which would equal square root of 5 minus, oh, this is 1/2, excuse me, minus 1 over 2 times R, which is what we end up with, which is what you'll see online. So here we did something with the, this infinite ladder circuit, and we don't really need that bit there. We did something with this infinite ladder circuit. So we used Kirchoff's laws to find the effective resistance of this circuit. It's a little more complicated than just writing out online something like 1 over the effective resistance is equal to 1 over the resistance plus 1 over the resistance plus the effective resistance, right? You can do this, and you can see how that looks very similar to something that we did over here, right? That's starting to look pretty similar. Not exactly similar, but it looks pretty similar. This uses the same principle as what I did here. Okay. Basically, here I said that the voltage drop from here to here is proportionate to the voltage drop from here to here because the circuit is similar, right? And that makes a lot of sense, right? We just have that voltage drop going down the line. Only here you just have you sort of invoke that, and all of a sudden you have it looks like magic. This, I hope, didn't look at all like magic. Even this doesn't look like magic. You say, okay, we keep on going down here. We lose some proportion each time because it's self-similar. We lose the same proportion. Okay, and we could have, and like I said, that argument is exactly the same argument they use online to get this one. If you don't understand why, you should think about that a little bit. Try doing both and stuff like that. In fact, I do have a problem A2, I think, that has the resistor-capacitor combination instead of the resistor-resistor combination, and you can try that instead. It's a little more fun. So this works out very, very nicely and really shows how both that symmetry works, and it's one of the few places where we really, really use those these infinite series that you spend so much time on in math class and in math methods and don't actually end up using them very often for some reason. So I hope that makes you happy too. You get to use all of these things that you were taught in all of these classes. I mean, people are not wasting your time in these classes. These things show up, they are useful, and they're things you can use in the future. So please make sure that you understand this thing, okay? Especially the Kirchoff's laws part, right? And I will see you in class. Bye now.